en esta red de un invitado muy especial, que es el tataranieto sobrino del gran padre de la mecánica clásica. Sin embargo, tenemos que presentarlo y tenemos que mencionar acerca de los que conforman la red también. Bien, se comunicó con nosotros el palestrante del día de hoy, que es muy especial, como les mencioné, casi descendiente de lo que es del padre de la física, uno de los padres de la física, gran amigo mío, que es el doctor Peter Newton. Para presentarlo, el doctor Peter Newton realizó sus estudios de undergraduate studies, sus estudios de pregrado, en la Universidad de Cambridge en el año 2008. Luego sacó su maestría en ciencias en el 2012. Yo recuerdo que lo conocí en el año 2012 cuando ya estaba empezando su PhD, su doctorado en física. En aquel momento me dijeron para yo supervisarlo, pero en ese entonces yo viajaba mucho, tenía que viajar a Tokio, y entonces él quedó bajo la supervisión del profesor Crispin Barnes. Entonces, sin embargo, estábamos en el mismo grupo de investigación. Luego regresé yo de Tokio y ya empezamos a desarrollar trabajos en conjunto, investigaciones en conjunto. Uno de los proyectos en el cual me llamó la atención es un proyecto que estaba relacionado con el germanio, el semiconductor germanio. Se trataba de repotenciar el germanio. Recuerdo que en aquel proyecto intervenían la Universidad de Southampton, la Universidad de Warwick y la Universidad de Cambridge, con un gran financiamiento. Quien realizó bastante en ese proyecto fue justamente el doctor Peter Newton. Me dejó con la boca abierta, en el cual hizo toda su tesis y todo el proyecto básicamente él, ¿no? Y luego de trabajar mucha amistad, he tenido la oportunidad de llevarlo a Perú, a traerlo a Perú. En estos momentos estoy en Perú, a traerlo a Perú muchas veces para que dé charlas en universidades, y ahora nos tiene con su presencia. Sin embargo, el día de hoy, el doctor Peter Newton me acaba de comunicar, está presente aquí, me acaba de comunicar que el día anoche le ha dado COVID. Pero vamos a tenerlo, vamos a presentarlo y vamos a preguntarle si es que está en condiciones de dar su charla o no. Perfecto. Si no, lo presentamos a todo el grupo y luego tratamos los puntos de la red, algunos puntos que tenemos. Primero, entonces, a presentar al doctor Peter Newton de la Universidad de Cambridge. Doctor Peter Newton, good morning. Your camera, please, Peter.
Hi, Lewis.
Hi, Peter. Sorry. First, we want to introduce you to people and to ask you if you are in the conditions to give a talk or not. How is your health with the COVID?
I'm pretty sick, but I can give it a go if you want.
Depends on you. If not, we can postpone that for other month. Depends on you. The health is most important.
Oh, I'll start giving the talk and we'll see who we get to, shall we? Let's do the talk.
Okay, yeah. In that case, I will introduce you briefly to the people here first, okay? Para presentarle. First, I will introduce you. Cada vez que presente a alguien, por favor, abre su cámara, ¿sí? Professor Ángel Bustamante Domínguez, who is the Dean of the Faculty of Physics of the University of San Marcos. Your microphone. Su micrófono.
Good morning, Dr. Peter.
Morning.
Peter, Ángel Bustamante is one collaborator of the TFN group for many years, even when the time of Tony Blunt, even. Well, thank you. And now, Professor Albino Aguiar from the University of Pernambuco. Albino?
Good afternoon, Peter. It's a pleasure to meet you.
Good afternoon.
Let I see your talk.
Professor Albino Aguiar, who from the University of Pernambuco, in Brazil. He visited the TFN group in the University of Cambridge, in the Cavendish Laboratory, around 7 years ago, roughly, to Crispin Barnes. También also we have Professor Isaías Gonzaga de Oliveira from the Federal Rural University of Rio Janeiro, from Brazil. Isaías?
Oh, hello, Peter.
Hi.
Nice to meet you. Nice to meet you.
Nice to meet you too.
Well, Professor Isaías Gonzaga Oliveira is also a very close friend, a collaborator. He specializes in modeling of superconducting vortices. También tenemos al profesor Ricardo Celis de la Universidad Nacional de Barranca de Perú.
Good morning,
Morning.
Dr. Peter Newton. Good morning, all the friends of here. Thank you very much.
Good morning, Ricardo.
Professor
Thank you.
Professor Ricardo Celis is from the University of Barranca, you know, and we have a publication with him in Applied Physics Letter, and you met him in the University of Barranca. Now he is also linked with the University of San Marcos through a project about superconductivity, where he is as an external member, the University of Barranca.
Thank you. Thank you.
We also have Professor Felipe Mundaca from the University of San Sebastián of Puerto Montt, Chile.
Hi, Peter. Nice
Hi.
to meet you.
Good morning.
Good morning.
The specialty of Felipe Mundaca is AB initio and modeling of many process of physics. The representative of in Venezuela from the University of Zulia, I think it's in Maracaibo in Venezuela, is Professor José Fermín.
Good morning, Mr. Newton.
Good morning.
Buen día para todos. Buenos días para todos. Gracias.
Thank you.
Buenos días, Femi.
Bom dia, Bino. Bom dia, Sergio Resende. He was my advisor in Recife.
Yeah. Also, we have from the Colombians, the University Nacional of Colombia, Professor David Landinés, I don't know if it's here, and Professor Jairo Roa. Is Professor David Landinés and Professor Jairo Roa there? Is here? They are here? No? If not, no problem. No problem. I think that it is time to start, but again, the same question, Peter, don't worry. If you feel quite bad, we can stop and we can postpone. The health is more important. COVID is quite serious. El doctor Peter Newton en estos momentos está con COVID y le estamos preguntando si es que puede dar la charla o posponemos. No, Peter Newton, can you give the talk or no? Depends on you, no problem.
Yeah, I'll give the talk.
Okay. I forgot to introduce you, the last one, Professor Arturo Martinez from the Simple Staff of Mexico. Arturo.
Hi, good morning.
Yeah. También, thank you. Also our invited panelists is Professor Sergio Resende and also Professor Carlos Alberto. Well, okay, we can start now. You can share your screen, Peter Newton, and start your talk.
Hopefully that is the right thing, yes?
Yes, go ahead.
Great, thanks very much, Lewis. Thanks for the invitation and thanks for the kind introduction. So in the talk today, I'm going to briefly outline this technology, the composite element magnetic barcodes that I worked on over the last few years, and talk generally a bit about how they work, how the technology is supposed to work, and then go into a bit more detail about what I have done on their magnetic properties, and we'll think a bit about how they can be optimized. So so obviously I need to thank a bunch of people before we get started. various people at Cambridge and a diamond light source who helped with this work and helped with the beam time measurements I did. And then on the so Crispin, my supervisor, Massimo, Niall and Sabrina, who came on the beam time, and then the beam line scientists at Diamond. And then on the right-hand side of the publications our group has made on this technology over the years. This is just a selection of them. So the top two are ones that I have written, and then the ones below that are ones that were written before I was involved in this project. So it goes back quite a long way, this technology, and it's been kind of iterated on over time. Okay, so what are these technologies, and why do we think they're going to be useful? Well, we were thinking about making technology to make water quality testing a bit more achievable, particularly in rural areas. So the current techniques you have for water quality testing are very accurate, precise, but they're very expensive. You need access to very sophisticated technology. So usually what you're doing is you're collecting samples and you're having to take them to a central lab somewhere in order to do these tests on them. As I say, we have to move these things to our central labs so that everything is ex situ. It would be great if we could do something in situ at the site to a similar sort of standard that can be done in central labs. And all these things are quite inaccessible to local people in their communities. You require people to come in and do this sort of testing for you. So is it possible that we can design something inexpensive in situ or kind of by a riverside, and that can be performed by people who are less scientifically trained than are typically needed for current technologies? Okay, so this is where our magnetic barcode technology comes in, and there's some just sort of ideas that I'm going to talk about a bit in this talk that is useful for me to introduce. So we're going to talk a bit about multiplex assays. So it would be ideal if we could test for many different things simultaneously. It's good to have a test that can test very well for one thing at a time, but that's obviously very time consuming. And often when you're doing these sorts of analyses, you want to be looking for many different things at once. So the idea of this magnetic barcode technology is that we will be able to do a multiplex assay testing for many contaminants simultaneously. And then going a bit later into the talk, we're talking about these magnetic properties, which will be talking a bit about shape anisotropy, dipolar interactions, and I'll also touch on how you're going to get a readout from this magnetic device. Okay, so let's go into some detail then on what this technology is and how we think it might work. So if we have some sample that may contain a large number of different molecules or contaminants in it. So here we have a series of different shapes and colors. Each one of these throughout this kind of pictorial demonstration represents some different molecule or ion that is in our sample that we want to test. And so we suggested that these sorts of things could be impurities in water, particularly what we were thinking about, but also other kind of contaminants in samples that we might be able to test for. Okay, so in order to be able to test for each of these target molecules, we would want to have some sort of probe molecule that corresponds directly to that. So for instance, over here for our blue star, we would have this corresponding probe molecule that would fluoresce when it came into contact with the blue star target molecule. But the key things with this are that each of these probe molecules has to be very specific to the molecule that it is targeting. So for instance, this probe molecule, the blue star, cannot fluoresce when it comes into contact with any of these other molecules that might be in the suspension that we outlined before. And similarly, we don't want any of these other probe molecules to fluoresce were they to come into contact with this target molecule. As this is quite a challenging thing to do, but there are developments in that area that lead us to believe this sort of thing is achievable. And other people in our research group have made developments on this. Okay, so assuming then we have a series of probe molecules that want to look for these different target molecules. Well, we assign each of them some sort of binary code. So for instance, here at the top, we see for the code 01000, we are going to have this red star probe molecule. And each of our probe molecules then gets this unique code. So the red circle is all zeros. And then, for instance, this green triangle probe molecule is 0 and then 4 ones. And you build up this database of all these different probe molecules. And what we're then doing is we coat our microscopic tag with those probe molecules, and we write that barcode, that binary code, onto our memory. And so what you're left with is a series of coated tags, each with a different binary code written on it, corresponding to the probe molecule on its surface. And so then what you would do once you have all these different probe molecules outlined and correctly labeled, you would put them all into your sample and you would see what happens, basically. So we add our tags into the suspension. And as I was saying, if we get the chemistry right with the probe molecules, they will only fluoresce when they encounter their matching probe target molecule. So here the yellow star probe molecule finds the target yellow star, fluoresces, none of the others do. And we see here this one fluorescing and with its unique code. So then the final step, once we've done the chemistry and we've got our array of tags, some fluorescing, some not, depending on whether they found their target molecule or not, we can pass them along a microfluidic channel and read out the binary code that's written on it. So, for instance, when we feed these ones through, we would read out their code and we would see they're not fluorescing, and that would give an indication that that target molecule was not found in our sample. But this molecule here, we've already said, is in the solution, so that tag is fluorescing, and so we see it's fluorescing and read out the barcode. And we identify some quantifiable amount of that molecule as being in our solution. And so at the end of the day, we then have some basically little laboratory, a little multiplex assay that has given us our result that our solution contained this target molecule and none of the others. And hopefully, were the chemistry well enough designed, it will give you a rough concentration of that molecule as well. Okay, so that's all quite complicated. What are the steps towards getting us to something that works? Well, we need to be able to fabricate these tags and produce a large number of identical versions of them. So we want many of the same barcode with its probe molecules on the surface in one multiplex assay to allow us to do this test reliably. And we need to be able to produce these very accurately, such that they're identical, so that the next step is possible, which is the writing and reading of the code. By the way that these barcodes magnetically behave, we need them all to be very similar in terms of their lithography. If they're slightly out, we're not going to get the behavior that we're looking for. So we need to be able to make them all as identical as possible. And as I was saying, then we need to be able to develop a scheme that allows us to write and then later read out these binary codes that we say we want to write on the barcode. We need to be able to get this microfluidic transport working. So it's all very well being able to read out the code, but we need to be able to send the tags through one by one, such that we can read whether they're fluorescing or not, and read what the code is that we've written onto it. And finally, we need to be able to get this this chemistry on the surface working. So we need to be able to attach our probe molecules to our barcodes, and we need to develop it such that we can get this very specific test for our individual target molecules. So progress has been made on each of these. In terms of this talk, we're going to look mostly at what we're doing to optimize these magnetic properties, and I'll briefly touch on all of the others to give you kind of an idea of progress that's been made. So the main idea behind how the barcode works is it's simply a shape anisotropy. So our little magnetic elements are made of permalloy, a very soft magnetic material, and its magnetic behavior is determined by the shape we create. So I'm sure all of you know this already, but it's always good to remind people. If we make our magnetic material non-spherical, we induce easy axes onto it, and further modifications allow a fine control of these magnetic properties. So we're going to talk a bit about rectangles and a bit about rectangles with pointed ends as two different sort of ways that we might be able to do this. So why is this kind of shape anisotropy needed? Well, it's because of the way we have to write our code onto these barcodes. We want to be able to get all of our barcodes together that have the same probe molecule on the surface and write the correct code to them. And how we will do that is we have our barcode, and we're going to sweep a global field backwards and forwards until we get the code that we want. So we start off, and let's say the barcodes are magnetized, or it's in some random configuration. We can then sweep backwards and forwards to get the code we want. So if we sweep in a negative field direction past the this value here, H1. So H1 is going to be the coercivity of our highest coercivity element. If we go past that value, we're going to put all of these elements in the same magnetic state. So they will all say, in this case, have a label of 1, right? They're all magnetized downwards in this case. And then if we sweep back the other way to some field here that is greater than H2, which is the coercivity of the second highest coercivity element, but less than H1. And so what that does is it doesn't change the magnetization state of our highest coercivity element, but it changes all the others. And so that will give us the code 10000. Now, if that's the code we want, we can just put the field back to 0 and stop there, and that's fine. And we can carry on sweeping backwards and forwards until we have the code we want. So if we go back to H3, which is the coercivity of this element, we would leave these two the same and rewrite all of these as ones and so on. So what we have is a series of bits here that we can write a simple binary code to. And if we have n bits, we can write 2 to the power of n unique codes onto them. So we'll talk a bit more about this in a minute, but first let's just note that some work was also performed in the group on the readout of this in its microfluidics. We would send our barcodes down this channel over a TMR sensor, and that will give us a signal telling us about the code that's written onto it. This is very well-defined channel, just bigger than the barcode, such that it moves along in a nice straight line. And here's the sort of signal you get out of this. So you can see these elements passing through, giving a good signal on our TMR microscope. Okay, so as I keep promising, let's go into more detail then on the magnetic properties of our barcodes. So, as I showed you previously, we had individual small rectangles for each of the bits. That works in such a way as it allows you to write a nice code to your barcode, but when you come to read it out, these small elements give you a very small signal on your measurement, and so the higher coercivity elements become harder to read, and so the and another problem was that individual rectangles form multi-domain states, which limits the reliability of the writing, and also limits the total number of distinct bits that you can have, because you have to kind of introduce slack in your system to account for this kind of slightly irregular behavior. And so what was decided on was to change this design a little. So from previously, as I said, we had the single element design, and this is kind of a cartoon of what the domain structure looks like inside. So if we were to magnetize it all downwards, you would get these kind of states that don't all kind of point quite in the same direction. This was then replaced with this composite element design that is what we've stuck with since, where we're using the dipolar interactions between these elements to reinforce a kind of a more homogeneous magnetization state. It also solves this problem where our narrower ones had a smaller readout signal. Well, now our smaller elements are a large number of small elements, which gives you a similar sort of signal to the single large elements that we still have at the other end of the scale. So, for instance, in this particular scheme, we would have a wide 3.2 micron strip, and then all the way down to the bottom, you would have 64 50 nanometer strips, for instance. And so there's a number of different parameters you can play with here as well to optimize these properties, even just thinking about rectangular shapes. You have the length of the elements, which turns out doesn't have much impact once you get to a large enough length, which is not that surprising. You can change their width, obviously, and you can change their spacing, and of course their thickness as well. Okay, so what will this look like in a kind of actual device, and what sort of materials is this made of? Well, we have to make these step by steps. We've been starting off using a silicon substrate and then kind of growing everything up from there. So the important bit is what are our elements made of? Well, you have your adhesion layer to get it to stick to your substrate below, and then we have the permalloys, the magnetic layer, and another capping layer on top to prevent oxidization. And then in the final device, we would imagine putting this in a SU8 kind of shell to protect it. Although everything that I will introduce in this talk doesn't have that, because we want to maximize our signal strength from our magnetic measurements, although in theory we could easily put the SU8 on top if we wanted to. Okay, so can we make these? Well, yes, we can. So again, we start from kind of individual wide elements, and we go down towards multiple narrower ones. So this is an SEM image of a device from this publication in APL. We have our widest element here is 3.2 microns wide, all the way down to our smallest here, which is shown more magnified in on the right hand side here, where we have 100 nanometer wide strips separated by 100 nanometers. And you can see these are quite well defined. There's some kind of non-homogeneity along their length, but in general it's pretty good, and we find that these small imperfections don't make too much difference actually. Quickly, we also checked that we could write something to this, so let me explain what we're looking at here. This is an MFM image of what we were just looking at, but rotated. So this whole thing's rotated clockwise by 90 degrees. And we're looking, hang on. Yes. Okay, it's a bit backwards as well, isn't it? But here is a 2-element bit, a 3-element bit, and a 4-element bit, if you can see that. And what we've done here on the right-hand side is I've written all of these in the same direction. So these are all magnetized to the right. And then in A over here, I've flipped the direction of this one, so it's magnetized to the left, and we can see that quite clearly from our MFM. So that works nicely. So we also, as I discussed before, put some had some designs with pointed elements. I'll just explain kind of what the parameters are for this, and then I'll talk a bit more in detail about them in a second. Again, we have our rectangles, and then at the end we put this point with a well-defined pointiness P, which is the length of the point, so from the tip to where it meets the rectangle divided by the width. And we find that this pointiness is actually the thing that matters to give these their properties. Okay, so we want to measure these magnetic properties. So we're going to use a magneto-optic Kerr effect magnetometer to do so. So this is the system I used. We have our laser over here, a polarizer. It comes into the sample, which would sit here in the middle of this magnet, and the laser would bounce off and come over to your photodiode on the left here through our analyzer. And we're using it in this longitudinal geometry. So the Kerr effect allows us to obtain the hysteresis loops of these structures. And we get very square hysteresis loops coming out from this, and this system works very nicely for measuring that, for measuring the ellipticity induced by this magnetic surface. Okay, so as I discussed when we were talking about the way we write codes to these structures, the important thing magnetically is their coercivity. Once we get above that, and given they have very square hysteresis loops, once we get above that coercivity, that's the point where we're able to change the magnetization direction. So what we need to be able to define when we're making a series of structures is bits with well-defined coercivities that aren't going to be confused with their neighbors. So this is a little confusing as I've missed the legend off. So our blue elements here are purely rectangular structures. So let's look at this one here, for instance. If we go down, that has a width of 800 nanometers. So that would be a structure with 4 strips, each of width 800 nanometers. So we can see here the blue hexagon is our average coercivity for a series of 5 or 6 of these that I measured. And individual readings are the little green circles that are with them. And so we see a very low spread over most of this range. The single individual 3.2 micron structure has a bit more of a standard deviation as seen on this log plot. And we see quite a low standard deviation over the rest of the range. What we also see is this structure here, which is kind of strange, which we weren't expecting. So once we get to a width of about 200 nanometers, instead of continuing with this narrowing and increasing the shape anisotropy, increasing the confinement and making the coercivity bigger, we see that as we narrow it, instead the coercivity drops for a little while. That is something we wanted to think about a bit more detail. We also then on this graph have these black points, and this is our pointed elements. And these are elements where p equals 2, so we have quite a long point on the end. And again, it's the same thing here, where the black squares are the average and the pink circles are individual data points. And again, we have a kind of similar sort of spread around the mean, and we see a single power law behavior along this trend line that I've shown in red. That these elements adhere quite strictly to. As this is a clear advantage over this in terms of a device application. Instead of this kind of drop-off area here, this crossover between these two different regimes, seemingly, we have one single power law over the whole range. So we want to think about why we get this behavior. Why in the rectangular elements do we get this little dip here in the coercivity around 200 nanometers, and we don't see that in the pointed elements? Well, we thought about this 2 ways. So we went to the Diamond Light source in Oxfordshire to do XMCD PEEM. So that's a way of seeing a magnetic contrast from an X-ray measurement. So polarized X-rays are incident upon the sample, and what you see in your PEEM image is a contrast between the 2 polarization directions that are have a projection in the plane of the sample. So let me explain that on the next slide a bit more detail. This is what the structure looked like at Diamond. Okay, so let's look at this single element on the left. This is one large rectangle, 3.2 microns wide, and we have our X-rays coming in from the right here. And so what we see in our contrast is our negative signal corresponds to magnetization in the opposite direction to this incident X-ray in the plane of the sample, and a blue would correspond to being in the same direction. So what I did before this measurement was I magnetized this upwards, and so we're not seeing that large magnetization along the body of the element. We're just seeing the perpendicular structure at the ends. What is happening here? Well, we're seeing a rotation in the magnetization at the end of the element. And this is more clear on our vector map here. So these little arrows are on this, hopefully you can see that, correspond to the direction the magnetization is pointing in at that particular point. And this color map is showing us as well, kind of at each individual point, where the magnetization is pointing. So along the body, as I said, I magnetized it along its length, along the easy axis. So they're all magnetized to the left. And then again, at the end, we get this incomplete flux closure domain. So we see a rotation upwards at the end. So what we're seeing then is a rotation kind of one way just below the end, and then a rotation much more the other way at the very end. So in order to see this in more detail, we compared these XNCDP results with some results from simulations. So these are Micromatic Simulations from a package called MuMax, which is very good at this sort of simple geometric structures. And so let's go through this figure here on the left step by step. So we have different single rectangles of different widths. So at the top, we have our element that we've been looking at that's 3.2 microns wide. At remnants, we see a full rotation to the right in this kind of incomplete flux closure domain at the end, as seen by this green color and these arrows pointing fully to the right. As we narrow these elements, we don't see the same thing anymore quite. So at remnants, instead of having a magnetization completely pointing to the right, it's canted kind of diagonally a little. And again, we see that for even narrower elements, it's much more canted. And we're also not seeing this darker blue structure in these narrower rectangles either. And then when we're applying a field anti-parallel to the majority magnetization direction, so along this red arrow, so these are magnetized largely upwards, as we can see from the blue color. But if we apply an external magnetic field downwards to try and switch the magnetization, we will see this magnetization pattern evolve. So this 1 millitesla structure here is just below the coercivity, and we're seeing this structure kind of push down from the top until the reversal kind of initializes in this yellow area here. I'll have a movie of this in a second. This is not quite what we see for all the other structures. So we see a similar sort of thing for the 267 nanometer version here, where we have something originating in the middle here. And then that reversal kind of pushes it down from there. But in the very narrow structures, if you see the kind of very top left-hand corner, this just below the coercivity points fully to the left, fully to the right, sorry. But for our wider structures, it's still canted. And so this is the origin of that kind of kink in the coercivity versus width plot I showed you earlier. We have a change in the origin point of our magnetization reversal when we apply a field that is anti-parallel to the majority magnetization direction. instead of kind of coming from this structure in the middle as it has the wider elements, it now starts to come from this structure in the corner. And so hopefully this will work, and I will be able to show you a video of this. So in the wider structures, we see this kind of pushing along from the middle, and this reversal kind of pushes its way down the structure. So let me explain a bit more detail what we're seeing. So this is what happens when we increase the external magnetic field from just below the coercivity to just above, and we then watch in time what happens to that. And our color wheel is here showing the direction of the magnetization there at each point. So it starts off magnetized to the left, and we are magnetizing it then to the right. And so, as I said, this structure from the middle just pushes its way along until that switches the magnetization direction of the whole element. For our narrower structures, that's not what we see. It's a lot more chaotic. So instead of seeing something from this middle structure, we'll be looking in the bottom left-hand corner. And that is where our reversal is initialized. As I said, much more chaotic sort of behavior. And again, we get our kind of incomplete flux closure domain reappearing at the end. So again, coming from the bottom left-hand corner and sort of working its way along the strip from there. And so these two different regimes of reversal explain our two different areas on that coercivity versus width plot I showed earlier. Okay, so that's all very well. But these aren't single narrow rectangles, as I said. That doesn't work very well for readout. So these are arrays of structures, and they're going to be affected by dipolar interactions between them. So how is that going to have an impact on our hysteresis? Is this going to change things at all? Yes, it is. So let's look at this hysteresis loop. Let's imagine that we're coming along the bottom here. We're magnetized downwards, so that's in the red direction, and we're going to apply a field upwards along this in the blue, light blue direction, as shown by this arrow here in the positive y direction. So we have we can simulate the hysteresis loop, and we can look at the kind of metastable magnetization configurations at each of these points in the hysteresis loop, were we to pause our field sweeping at these points. And so initially we start to see the first elements at the edge of the array reversing by the method I showed in those movies previously, until you reach something like this, where the these domain structures at the ends of the rectangles are anti-parallel. And what happens there, instead of kind of continuing to undergo reversal, they get kind of pinned. And so the dipolar interaction here prevents this from changing direction. And what's happening is that we have a dipolar interaction between this part here and this part here that kind of reinforces them in the negative y direction and requires more field then to cause them to actually reverse along the whole rectangle. As then we increase the field by another millitesla step, and this one goes. But again, we're not seeing the whole lot cascade. We start to see some more. And if we increase the field further, so more of them start to go. But we're still seeing some that are kind of in the middle of the structure, they're getting pinned. So this is not ideal. If we want something that we can write to reliably, consistently, we don't want to have some elements in our array reversing their magnetization at different fields from others by something that we can't control very easily, which is the direction of this domain at the end of the strip. rather than something that is induced by our lithography. So this is going to make it harder for us to create a memory with lots of different uniquely writable bits. We see as well a kind of, this is more XMCDP data at the top, it's kind of chaotic in what you get in terms of these structures at the ends of the rectangles. So this is just me sweeping the field up and down in these elements and seeing what happens. So these are magnetized down, I think. That doesn't really matter. So I'll be applying a magnetic field up the positive y direction to reverse them, and then back in the negative y direction again to reverse them back. And you don't see the same state coming back again. You get some kind of pseudo-random arrangement of these structures at the ends of the rectangles. They look like they, more often than not, align with the neighboring one, but not in a way that's kind of useful. So if you compare this to the result of simulation, even if you do everything perfectly, if you apply too much field, what you find is that this structure at the end can just reverse itself, even if you apply a field directly along the y direction. You might think, well, if you're applying a field that's slightly off the y direction, that's causing these to change. Well, even if you apply it directly along the y direction, these structures still change. It is a consequence of dipolar interactions between these neighboring elements. So you could work to improve this by applying your field slightly canted to the y-axis, but it's not very reliable. I still think you would find some effect of this kind of pseudo-random arrangement of these domain structures. And so this is where our points elements come in. The structures at the end of these remnants are canted much more along the point, and the method for their magnetization reversal is quite different. As we discussed before, it gives you this single power law dependence because it doesn't do the same sort of structures we discussed here. So this image shows each of these individual elements. This is the top element in each array, sorry. So these are not just isolated, these are the top elements in an array. And what their magnetization structure looks like just when they're subject to a field just below their coercive field. And we see these kind of structures in the middle that's kind of consistent across the range. And so what does that look like if we kind of play a movie of how the reversal happens? So again, we're just at a field that's just below the coercivity in this still image, and then we increase it to just above the coercivity, and we watch in the time domain what is happening to our magnetization structure. So this is the top of our array. So this is an array of 20 elements of width 160 nanometers. And we can watch what happens, hopefully, if it goes. There we go. So we see the top one moving first, then the next one, then the next one. It cascades very neatly all through the structure all at once. So let's go to that again. So it starts here and it cascades all the way down to the bottom and they work their way all the way along. So this is a much more neat and reliable way of making these structures, and gives you much better magnetic properties. As I discussed previously, gives you this single power law dependence on coercivity and strip width, the kind of the key result of this. So well, what could we do in the future to optimize this further? We're looking at the effect of the separation of the elements, as I discussed near the start. That's a parameter you can change. We expect it to have some impact, although actually that impact to be quite limited. It will affect the dipole interactions between elements in your array, but that's probably not going to make a big difference to your magnetic properties, but it's something you can play with. And ultimately, in the next steps of getting this towards a usable technology, we need to finalize some design for this barcode that you could read reliably in flow and containing enough bits that we could carry all the information we wanted to carry. And as work has been underway to try and combine these with tests for heavy metal contamination in water. And so some work in our group has been performed on developing a mercury test that one could coat to a gold surface that you might put on these barcodes. In the longer term, then we want to be able to use these barcodes in a multiplex chemical assay. Just some sort of proof of principle of being able to do multiple at once would be a really big milestone in this sort of technology. Okay, so in conclusion then, we've created a versatile non-volatile magnetic memory, and we think we could probably store roughly a 12-bit binary code given the progress we've made to this point. We've shown that we can write simple codes to these structures. We've shown using XMCDP measurements and micromatic simulations that we understand in quite some detail at this point exactly what's going on magnetically in these structures, both at remnants and during the process of their magnetization reversal. And we've used that information to further inform our designs, moving towards these kind of pointed elements rather than the purely rectangular ones. So as I say, we're going to these pointed elements, we're thinking about the impact of this strict shape, and that allows us to further refine our design. Okay, thank you very much for listening.
Well, thank you very much. Thank you very much, Peter Newton. Muchas gracias, Peter Newton, por darnos la charla, a pesar de estar con el COVID. Pasamos rápidamente a las preguntas. Al público, muy rápidamente, si tienen alguna pregunta, dejarlo en las redes sociales donde están siguiendo esta transmisión. Rápidamente, ¿ya? Para no cansar mucho al investigador Peter Newton, hacemos las preguntas brevemente. ¿Okay? Empezamos con las preguntas. We are going to start with the questions. First, with open your camera when you give your question, please. Abran su cámara cuando empiecen sus preguntas. Primero con first with the Dean of the Faculty of Physics of the University of San Marcos in Perú, Professor Ángel Bustamante. Ángel.
Thank you very much for your conference. My question is, when you have to work in magnetic materials, there is a special constant who depends on the form of your proof. The anisotropy constant, you evaluate this in your materials?
So we adopted in our simulations a well-known parameters of permalloy when we were doing our these calculations. So we in these mu-max simulations, you have to put in an exchange stiffness and a saturation magnetization in order to get out something that looks kind of sensible. And so by this is why it's important to do these things experimentally as well as the simulations. We can see that what we're getting corresponds between the two. So we have some faith that our parameters are the right sorts of things.
Well, thank you. Thank you very much, Ángel Bustamante. More question, Ángel? Okay. Okay, thank you very much. Ángel Bustamante is the Dean of the Faculty of Physics of the University of San Marcos. Now, the representative of the University of Pernambuco in Brazil, Professor Albino Aguiar.
Hello. Congratulations, Peter, for the nice talk. I have a bench of questions, but I'll just ask. I imagine that's not easy to make these barcodes and to have it reproducible. This is the first question.
Yeah, so if we look back at something like this to give you something to look at. These are defined by electron beam lithography at the moment. So in our department, we have a very good electron beam lithography system that allows us to reproduce these structures quite accurately, actually. Obviously, between different samples, you get a bit of change between properties, but largely that's you have to be careful with the thickness of the permaloy you're growing to give you something that is very reproducible, which is something we've not worried about too much at this point. But were this to become a technology, yes, those are the sorts of things you would have to think about.
Okay, thank you. Bye. Thank you, Luis.
Thank you, Professor Albino Aguiar. Now, very quickly, with a question from the representative of the Federal University of Rural Federal University of Rio de Janeiro, Professor Isaías Gonzaga Oliveira.
Thank you very much for your excellent talk, Dr. Peter. I don't have any question, but congratulations for your very nice work. Thank you.
Okay, Professor Albino Aguiar, Professor Isaías Gonzaga Oliveira, is there any question from the Brazilian public?
I don't have.
Okay, no problem. Okay, let's continue then with the other representative, the University of Barranca in Peru, Ricardo Celis.
Thank you, Luis. Congratulations to the Dr. Peter Newton. No question. Thank you.
Okay, any question from the public of the University of Barranca, Ricardo Celis?
Yes, bueno, ¿cómo podría haber alguna relation and the skirmions magnetics materials with the código de barras and effects Kerr and Faraday? What your exposition here?
I didn't quite catch that, sorry.
Luis,
Could you repeat?
Sí,
okay.
Sí, por favor, ¿le podrías mencionar si es que hay alguna relación entre los esquirmios magnéticos y lo que ha presentado hoy día el doctor Peter Newton? Gracias.
Peter, can you study the skirmions, magnetic skirmions with your in these barcodes or any signals?
So they're not. It's not the right sort of structure to create skirmions. You're looking for something with different magnetic properties to be able to form a skirmion lattice of some kind. This is much more designed in order to be able to not see that sort of thing. In fact, to be able to see a very uniform magnetization.
Yeah.
Okay, thank you very much, Ricardo Celis. Unfortunately, we have too much time. Thank you very much. Now we continue with the representative of Chile, Professor Felipe Mundaca from the University of San Sebastián, Puerto Montt, Chile. Felipe.
Yes, here. No question here.
Any question from the Chilean public?
Tampoco.
Okay. Professor Arturo Martinez from Mexico mentioned that there is no question from his side. However, if there is any question from the Mexican public, Arturo? Arturo Martinez? Not here, I think. Microphone, Arturo. Okay. Microphone failing. Okay. Well, okay. Now we have also another member who usually is here, Sergio Conejeros. Sergio.
Hi, I'm here. Thank you very much for your talk a bit. So I have just one question about the composition of the magnetic thin film. Is there any particular reason why you are using nickel and iron for?
It's just because it's a soft ferromagnet, basically, that allows us to control the properties as much as possible with shape anisotropy. The person who worked on this project before me, so that would be, let me move to this slide. So that's this paper here, this RSC Advances paper, I think goes into a bit of detail about different magnetic materials you might want to use.
Okay.
And permalloy is the clear best of the ones that they tried. So.
And I think is it also cheap, right?
Yeah, and it's easy to grow. I can just grow it by thermal evaporation, not very, in a very kind of rough kind of vacuum. It's nice to work with.
Oh, okay. Thank you very much.
Okay, thank you, Sergio Conejeros. Now, apparently, Professor Arturo Martinez is telling us that there is a question from the public. The Mexican public says that, can you compare the barcode technology with other techniques for heavy metal detection?
Yeah, that's a very fair question. I would say we're not there yet. This is still a bit away from being a workable technology. As I was saying in the introduction, the advantages are that where it's a work, you could do things in situ or in the field, and it shouldn't need the kind of big scale labs. And we have got some chemistry that does give us the right sort of behavior, but we're not there yet where we can use this as a heavy metal detection technology.
Okay. Now we have the representative from Venezuela, from the University of Zulia, Professor José Fermín. José Fermín, quickly, please.
Gracias, Luis. Thank you, Mr. Newton, for your excellent talk. By the moment, we have no questions for you, and just to say you have quickly recovered.
Thank you.
No question as well from the public of Venezuela, José Fermín.
No, there are no questions from this side of the world.
Okay, there is not the representative. Thank you very much, José Fermín. No representative from Colombia, Professor David Landinés, Professor Jairo Roa. I think that they are not here. Ximena Velázquez.
Sí. Good morning, Professor Luis. In this moment, we don't have question for this webpage, but we only have to say thank you for the for this today.
Okay.
For this
okay, don't worry. No question from the Colombian public. Well, Peter Newton, by the way, Ximena Velázquez is from the University of Colombia, and she's going to visit the Cavendish Lab next year.
Okay.
Yes, Ximena Velázquez is a PhD student. Also, another Peruvian student from the University of San Marcos is Henry Sánchez. They are going to visit as well the next year the TFN Group. El otro año, Ximena Velázquez, estudiante de doctorado de la Universidad en Colombia, y el estudiante de doctorado de la Universidad de San Marcos, Henry Sánchez, están visitando la Universidad de Cambridge. Bien, we have some invited panelists, a couple of them. Professor Carlos Alberto from the University of Sao Paulo. Any question? Camera, please.
Good morning, everybody.
Could you activate your camera, please, Carlos?
Yes, just a moment, please. Oh, I'm having trouble here.
Okay,
I'm
go ahead.
sorry.
Don't worry, go ahead.
Thanks everybody for inviting me to this talk. Peter, I have a question for you. When you showed a figure with linear behaviors, there is a kink in a blue curve. I didn't quite understand that. But yes, this curve.
Yeah.
Could you explain that for us? Please?
Yes. So it's because we have two kind of different regimes colliding. So you have this from basically this point up to here, and from this point down to here are different regimes of this reversal. So this is to do with this movie I showed. So these are the two regimes. So the bottom right of the image is this kind of behavior where we have this reversal nucleating in the middle of the rectangle and pushing its way kind of
I see. Thank you very much.
Along, and then the other end is this chaotic behavior where it nucleates in the corner and branches out from there.
Oh, okay. Thank you very much. Very nice.
Thank you, Carlos Alberto. Thank you, Carlos Alberto, from the University of Sao Paulo. Also, we have another invited, the last invited panelist, Professor Sergio Resende from the University of Pernambuco. Sergio is there. Are you there? Otherwise, we'll finish. Okay, no more panelists. Okay, well, now, if there are any question from the public of the University of San Marcos, Melvin, preguntas del público de la Universidad de San Marcos en Perú.
Saludos, profesor. Saludos, doctor Peter Newton. No hay preguntas por Lares.
Bien, ok. Para mencionar rápidamente también que hemos comprado un microscopio de fuerza atómica, microscopio de fuerza magnética, para el laboratorio en la Facultad de Ciencias Físicas de la Universidad de San Marcos, y podemos quizá replicar estas medidas que hace el doctor Peter Newton. Peter Newton, we have bought in the University of San Marcos one MFM, and also we yes, and also we have downloaded the program, the MUMAX that you mentioned, and for the students are going to try that as well, try to replicate your barcodes. Okay, well, thank you, Peter Newton. I want to mention very quickly just to finish about this group, this network. This is the network. Thank you. This is the network of Latin American network of physics, matter condensing physics, and material science. Is many universities in Latin America, and I will mention briefly one news. Brevemente, unas noticias breves. La semana pasada los últimos días he estado visitando Ayacucho, en los cuales la universidad en Huanta que está transmitiendo esta charla, ha transmitido esta charla a la Universidad de Huanta en línea. A través de sus autoridades mencionan gentilmente que el próximo año podríamos quizá realizar la segunda versión de la Conferencia Latinoamericana de Superconductividad y Magnetismo en Ayacucho, Huanta. Gracias a las autoridades, los cuales se van a internacionalizar. Esta es la Universidad Autónoma de Huanta en Ayacucho. Estamos buscando el financiamiento y prontamente vamos a tener más novedades para realizar la segunda versión de la conferencia. Bien, brevemente también, very briefly also, Peter, you are also invited for the next talks whenever you want to join us. La siguiente charla va a ser el 15 de octubre de Armando Navarro de la Universidad Federal de Pernambuco, el 22 de octubre de Sergio Resende, también de la misma Universidad de Pernambuco, el 29 de octubre el profesor José Luis Ochoa del Instituto Venezolano de Investigaciones Científicas, va a ser el moderador el profesor José Fermín. El 5 de noviembre el doctor Adrian Ionescu de la Universidad de Cambridge ha confirmado ya, pero va a hacer su charla a partir de las 9 de la mañana, en el caso de Adrian Ionescu. El 12 de noviembre, el profesor Diego Lamas, de Argentina. El 19 de noviembre, el profesor Edson Sardela. El moderador va a ser el profesor Isaías Gonzaga Oliveira. El 26 de noviembre, el profesor Sergio Conejeros Espíndola, de la Universidad de Antofagasta de Chile. El moderador va a ser el profesor Arturo Martínez. El 3 de diciembre, el profesor Leopoldo Suencún de Uruguay. El moderador será David Landinés. El 10 de diciembre, el profesor Alexander Polasek, el profesor Isaías Gonzaga Oliveira va a ser el moderador. Y finalmente, último día de última charla en diciembre, el 17 de diciembre, el profesor Carlos Santos de la USPI, el moderador será el profesor Albino Aguiar. Luego tomaremos unas vacaciones, after that, some holidays por Christmas, New Year, and then estamos empezando quizá a los fines de enero, por unas semanas. Perfecto. Entonces, well, thank you very much. We special thanks to Dr. Peter Newton because he has COVID. Nuestro gran agradecimiento al doctor, nuestro gran amigo también Peter Newton, que lo conozco desde 2012, buen amigo él, y también es por su linaje también de la física clásica, etc. Es un buen amigo y al día de hoy, a pesar que ha sido detectado COVID ayer, nos ha dado la charla en esas condiciones. Muchas gracias. Thank you very much, Peter. We are going to everybody open their camera, please, to say goodbye to Peter, everybody, and we can see us next week. Say goodbye to Peter, please, everybody.
Bye, Peter. Thank you for your talk. Bye.
Bye.
Bye, Peter. Thanks.
Goodbye.
Okay.
Peter, goodbye.
Okay, thank you very much, Peter Newton. Thank you very much for your talk, even that you are with COVID. Thank you very much, and we're sorry for disturbing your day. Get well soon. Get well soon. Okay, thank you. Okay, cortamos la transmisión. Finalizado. Hasta luego. Chao.
Hasta luego. Hasta luego. Gracias.
Hasta luego a todos.
Hasta luego. Melvin, cortar la transmisión, por favor.